Enterprise Campus Design, Multi-Layer Architecture and Design Principles. Thank you very much for joining the session. Welcome. I'm very excited to see such a great audience. This session is all about Campus Design 101. We're going to be talking about L1 and going up to L7. And the main focus is going to be the architecture part of campus design. We're going to talk about core access and distribution and all the interaction between different layers. And we also will be talking about different design principles and how the combination of features will drive the network resiliency and scalability. The most important thing, this is all foundations. So as long as we build the foundations right, everything that we build on top of it is going to be rock solid. And this is our goal, build the rock solid networks. The network needs to converge in sub-seconds, and this is our goal. We're going to be chasing today every single millisecond and show you how the different architecture decision will impact the overall network convergence. My name is Marcin Hamrus, and I'm the part of the CX professional services team. I'm the principal architect. I've been at Cisco for the last 11 years, and I joined as the tech engineer working on the campus and the Catalyst platforms. At some point, I moved to my current role, which is planning, designing, and implementing in professional services. For the last 5 years, I'm doing software-defined access. With me, my dear colleague Jaro, who is the principal engineer in TAC. He is one of the escalation leads for EMEA for Catalyst and Campus. And he has a huge experience, and he will be sharing a lot of best practices around the campus networking and how to design it well, how to implement it well. So the goal of the session is to present the principles on enterprise network design. We will be talking about the hierarchical approach. We'll be talking about layer 2 and layer 3 and what are the pros and cons between two. This session is very much focused on the wired aspect. The wireless is a different path. This session is not about any sort of overlays. We're not going to be talking about SD access, EVPN, or DNAC, or the cloud. However, from time to time, we'll be referring to these points, just making some references. This session is also product agnostic. So we're not going to be focusing on anything which is product specific, so anything which is scale or performance related. We will be focusing on the architectural aspect. So a couple of logistics things. There is a WebEx app. You can go there. You can join the discussion. This room will be moderated until the February 24. So we encourage you to join the session, to join the room and ask the questions. We will be trying to answer every single questions you might have. Also, because we have quite packed agenda, so I would encourage you to ask the questions towards the end of the session. So we'll stay here. We'll answer any questions you may also have. And we'll be available after the session just in case you would like to have a slightly longer discussion. So, starting with the agenda, we'll start with the campus vision and strategy. We'll cover multi-layer campus design principles, the most important aspect of this session. We'll be talking about foundation services, so all the different building blocks and the puzzles that we will put together actually in order to make the networks highly resilient, highly scalable, and secure. We'll cover best practices, and we'll wrap up the session with the conclusion. So with that, let me move into what's top of mind for Cisco when it comes to the campus and how the campus is actually evolving. So when we joined Cisco with Jaro 11 years ago, the sentence that Cisco changes the way we work, live, learn, and play was something very important for us, something that was actually top of mind. And since then, nothing has changed. What has changed is the rapid industry transformation. And what is actually happening, the whole shift towards the applications and how the applications are being currently developed, deployed, and consumed. So that puts a lot of pressure on the network itself and on the network design. Now, if we talk about the vision itself, If we talk about the application and the application-centric paradigm, this is something that is happening now, and even your experience here at Cisco Life is very much depending on the application. So now the question is raised, how network is actually supporting this transformation, how network is connecting all the different components and systems to drive the user experience. So this transformation is called digital transformation. And Cisco's strategy is actually to connect, automate, and secure your digital agility in the cloud-first world. Now, we know that with digital transformation, there are many challenges. And the challenges that our customers are facing, especially how do we support this digital transformation. So there are a couple of things. Number one, bandwidth-hungry and latency-sensitive applications. So because the new generation applications are consuming more and more, we are seeing huge demand in terms of the bandwidth. So if we take the example of 8K video, which is consuming up to 7.3 terabytes of data, up to 100 megabits per second per channel, it's a lot. But it's not about the bandwidth consumption, but it's about the latency and what we are doing with these applications. So how we are actually enriching this. Take the example, the WebEx transcription or online translation. And how do we actually engage with the stream? How do we compute it, process it, and re-engage? So that's unprecedented increase when it comes to the bandwidth and decrease when it comes to the latency. Another thing is the agility. So currently, the customers, the users are moving between the campus and the branches and the home office. And the applications are moving between the data center and the cloud. And the question is how actually the network is supporting these changes. And how do we make sure that we deliver consistent access to the applications? So we need to be kind of the enablers, not the blockers of these changes. And the network needs to support it, especially from the architecture perspective, but also from the operational aspect. So the number of changes that are happening currently, because of how the applications are deployed, it pushes a lot of pressure when it comes to the automation aspect. Another thing is the aspect related with all the new devices that we are connecting. So the IoT devices and the overall scale. So we need to make sure that the network is ready to connect all the different endpoints that we are currently connecting. And the most important aspect is the security. So first of all, we need to balance between the internal and external threat vectors. We need to deal with the new generation threat vectors that are more oriented on the lateral attacks, not the attacks on the data, but more on the infrastructure itself. We need to also, coming back to the IoT point, we need to make sure that our access layer becomes the first line of defense. So we should implement all the security measures at the access. So we need to build the networks that are reliable, they are scalable with the inbuilt security. Now we are embracing all these changes with software-defined networking, but not a kind of the book definition of SDN, where there is a central controller which is making all the forwarding and policy decisions. We are actually doing it with the distributed systems, where each and every independent device is making this decision on its own. So any policy decision, any forwarding decision is being done by the distributed systems. And that's another challenge. How do we make sure that all the different distributed systems, they are consistently configured, that they are consistently orchestrated across the network? So this is what we call intent-based networking, where the user is actually expressing the intent, business intent, and we are providing the tools. We are providing the tools that are translating that intent into the configuration. So intent-based networking, it actually consists in three steps. The first step is the expression of the intent. The second thing is the translation of the intent. There is an activation of the intent. And the last piece, which is very important, which is the assurance. So whatever has been pushed by the controllers, by the orchestrator, how it is translated, whether it is actually pushed to the devices. So in Cisco portfolio, we have a number of solutions from the data center, cloud, one. But today, we're going to be focusing on the campus. So we will be focusing on the DNA center, on the SD access, and the campus itself. Now, in the campus, we have what we call digital network architecture. And this digital network architecture consists of multiple layers, starting from this bottom one, which is where all the physical devices are connected, through the virtual layer, where we have all the routers, virtual routers, and virtual components. Automation and analytics is represented by DNA Center. And finally, the cloud service management is all about the integrations, all about the ecosystem, all about the APIs. Today, we'll be focusing very much on the bottom layer. How do we make sure, how do we build rock-solid network design and architecture in the campus? Because, again, everything that lies on top of it is going to be rock-solid, as long as the bottom layer is going to be solid. So with that, let's move into one of the most important topics, which is multi-layer campus design principles. So currently, I'm building a house, my own house. And for those of you who went through this process of building your own house, you can recognize how challenging the process is, how time-consuming, sometimes traumatic. So for me, it's actually a mix of everything, right? So, but I made a decision, a conscious decision, to build my own house. Now, you can build your house that looks like that, right? It's a house, right? It consists of all the components, like roof, windows, doors, right? It's a house, right? But does it serve its purpose? Well, if we think from the resiliency perspective, will it actually sustain if there will be like a heavy snowfall, flooding? I don't think so. If we want to expand it, well, probably I wouldn't touch it because I don't know what's going to happen, right? From the security, external security threat perspective, does it protect from anything? Well, I don't think so. So I use this analogy because it really resonates with my perception of how we should build the networks. We should build networks which are rock solid, which are built on the solid foundations, well planned, well designed, based on our architecture principles and design best practices. And this is what is the session all about. It's all about design best practices. So what we want to do is to provide you those tools that you will be able to build your network, which is rock solid, resilient, and secure. So one gentleman at some point said, if you fail to plan, you plan to fail. So if you fail to plan designing your network, which is solid, based on the solid foundations, which is resilient and scalable, you will fail at some point. And you will fail either on the architecture perspective, where your network will not be able to meet all your business requirements, or you will fail at the operational side, where your network will not be able to cope with the number of changes, right? Or it will not fail over in case there is some kind of the outage. So this is a very important sentence. We will keep repeating this sentence today. If you fail to plan, you plan to fail. So with that, let's move into hierarchical campus design. Hierarchical, so kind of back to basics. Hierarchical campus design is all about three fundamental layers: core, access, distribution. Each layer in this architecture plays its own distinct role. And there is an interaction also between all these different layers. The most important thing about this architecture is it's highly modular. It's highly scalable. So if you want to expand it, it's very easy to just replicate one of the distribution blocks, connect it back to the core, and horizontally scale, right? If you want to add additional security functions, or if you want to add additional one function, again, it's easy to replicate every single distribution block responsible for it and then scale it horizontally. The most important aspect of this hierarchical campus design, it is deterministic. So in case of any single link or node failure, we know exactly what will happen. We'll know how the network will reconverge. This is our goal. So how many of you have the network, or at least used to have the network, that looks like that? Can you raise your hand? OK, there are a couple of people. Yes, so this is the typical example of the network which grows organically. You start small. You start with just a distribution block with a couple of access switches. And then you keep adding. There is a requirement of adding additional building, additional maybe a firewall, maybe a data center. So you keep adding. But there is no real structure. There is no real hierarchy. And the biggest challenge of this network design is that it is not deterministic. It is not predictable. I'm not going to be able to tell you what's going to happen if any single link or node fails in this architecture. So we want to build the networks that looks like that. They are highly, they are hierarchical, and they are scalable. So with building hierarchical networks, you are getting a fundamental benefits. Sorry, it just keeps moving. You are getting fundamental benefits. First of all, you are creating those small fault domains, right? Each distribution block is your small fault domain. And by building your fault domains, you are actually isolated any potential software or hardware issues, or even the misconfiguration. You're isolating and not propagating it across the whole network. Second thing is, you are building a very predictable traffic flows. So you know exactly how the traffic flow will look like. When it comes to the troubleshooting aspect, you know exactly how the traffic will look like and how it will fail over in case of the failure. The third thing is you are getting the load balancing. So because of the way how it is built, each layer, which is each function at each layer is redundant, and there is a redundant connectivity between each layer, you are getting the load balancing. You can load balance, not like with the previous example where you cannot really load balance, right? Either it's on L2 or L3. And the last thing is you are getting a sufficient level of redundancy. So the access layer. The access layer is not only about connecting users and the endpoints. The most important aspect is that this is your first layer of defense. This is where you should implement the security measures. So I'm sure you know, or at least I'm sure that some of you have experienced a situation where someone brought a router, and this router started propagating the IP addresses, right? And people started losing the access to the network, right? So there are very basic features like IP source guard, DHCP snooping, dynamic ARP inspection that can really solve it really quickly. There are things like .1x or TrustSec that can enable the user authentication and authorization and segmentation to the network. This is the first line where you should think about these features. The most important thing about the access layer, this is the first layer where you should apply high availability. So thinking from the physical link perspective between the layers, upstream, you should enable it redundantly. Also, from the perspective of stacking it, from the perspective of potentially physically or logically stacking these devices, this is something where you should start thinking at the access layer. Distribution. I hope it will switch. Distribution layer. It's all about scale. It's all about connecting different access layer switches. This is typically the first layer. This is your boundary between layer 2 and layer 3, right? Because typically, if you have layer 2 access deployed, then your distribution is going to be the first layer. So you will need to apply some sort of first hop redundancy protocols, HSRP or GLBP. Now, distribution block, it's also about summarization. Not because of reducing the number of prefixes you have in the network. it's because of the convergence. Yaro will talk about it, how summarization can really improve dramatically the overall network convergence. This is why we should apply summarization at the distribution layer. And finally, the core layer. The core layer is all about performance. It's all about making sure that we are able, from the performance perspective, connect all the different distribution blocks and scale it horizontally. So the question is, do we actually need a core layer? Well, if you start small, if you start with just a distribution block and a couple of access switches, probably you don't, right? It is perfectly fine and valid design. You can add additional distribution block. It's still fine. It's just 4 additional physical links. It can be an endpoint distribution. It can be a server distribution block. Things are getting quite complex when you add the third block, right? Because you already here have 8 additional physical links and 5 additional IGP peers. So that's a lot. So you are having this additional overhead from the physical perspective, but also from the configuration. Things are getting really complex when you add the 4th block. Because in this case, you actually need to add 12 additional physical links and 8 IGP neighbors per each distribution node. That's a lot, and it doesn't scale. You cannot keep adding, basically. It doesn't work. So the core layer is not about additional boxes. The core layer is actually to simplify the connectivity between different distribution blocks. It's about having a very hierarchical design where we know exactly what will happen, so very predictable and deterministic. This is all about the core layer. OK, so we talked about different access, distribution, and core layers. We talked about why do we need the core layer. Now let's talk about the distribution block and what sort of options do we have. If I were to suggest or recommend a design which is simplistic, it's also deterministic, I would go with this approach, where there is a IP subnet equals VLAN equals access layer switch. IP segment, IP subnet equals VLAN equals access layer switch. With this type of design, we are bounding a VLANs to particular access layer switches. We can bound a data VLAN, or we can bound a data and voice VLAN, right? So what we are getting with that? First of all, we are limiting our exposure to a spanning tree. I'm not a big fan of the spanning tree, and in my experience, I've seen a lot of outages, not because of the spanning tree, but I've seen a lot of outages because of the bridging loops. Bridging loops that are causing the outages, the whole network down situations. So as much as I can, I'm trying to avoid using layer 2 and spanning tree. So in this case, this is the perfect example where we can actually bound it. We can limit our exposure to a spanning tree. Between the distribution blocks, we have layer 3. So what we are creating is a loop-free topology. And we are pruning VLANs for each and every access layer switch. In this case, we are really having only a set of access VLANs, connected to each and every access layer switch. Now, can you, or maybe, how many of you can think about a use case or the application where it requires layer 2 adjacency between 2 hosts? Can you raise a hand? Like any application or use case that requires a layer 2 adjacency between 2 hosts? There's one. There's a couple. Yes, so I can think about a couple of them. Building management systems, BACnet protocol, right? Wake on LAN, silent hosts, right? So that typically requires some sort of layer 2, some sort of broadcast. So when you have this use case like that, this design is not going to fit. It's not going to work for you. So we can have a hybrid approach. The hybrid approach is that for these specific applications, for these specific use cases, we'll have a VLAN that will be stretched across. and only for these specific applications. Everything else is going to be following the same model. Single segment, single VLAN, single access layer switch. So in this case, again, we are limiting our exposure to a spanning tree. We are stretching VLANs only where really necessary. And we have still vast majority of VLANs configured actually with the same approach. Right. In case you have the whole bunch of VLANs that you need to stretch, I would recommend this design, where you stretch all of the VLANs, but actually you completely change your distribution block. And your distribution blocks now, it's a set of logical boxes. So it's a set of logical box based on 2 physical boxes. So things like VSS or stackwise virtual, where you can logically stack them. From the access layer perspective, these devices, they look like a logical device. So you can apply things like multi-chassis Ether channel. You can leverage things like non-stop forwarding or stateful switchover. And you can get much better convergence because of eliminating things like first hop redundancy protocols like HSRP. With SSO, you're actually getting sub-second convergence comparing to first hop redundancy protocols. Now, if we follow the same rule of single segment, single access VLAN, single access layer switch, we have a very interesting option. This interesting option is called routed access. So with routed access, what we are actually doing, we are moving L3 function down to the access. So in this case, the access layer switch becomes the router. It becomes the default gateway. So we are completely, again, eliminating the spanning tree because there is no L3 in this L2, in this topology. We are eliminating first hop redundancy protocols. But the most important thing with this type of design, we are drastically reducing the overall convergence. So the best we can get with the layer 2 and spanning tree is around 800 milliseconds. The best we can get with the routed access is 200 milliseconds, with some sort of tuning, maybe with the additional BFD configuration. So it's really a huge improvement. Now, what's the challenge? The challenge with routed access is that you will have some sort of overhead from the IP allocation perspective. You would need to allocate a block for every single access layer. You also, in your IP schema perspective, when you plan it, you need to also think about those ports, the connections between the access and the distribution layer, because we need to think about the summarization and how you will summarize it later at the distribution block. But the biggest actually challenge is that you are losing flexibility. So you no longer, if the business comes and asks you to support this kind of backnet BMS systems or sort of systems like that, you're not going to be able to support them. So in this case, what's the solution? Well, the solution is overlay. The solution is overlay. With overlay, you are getting all the benefits of the routed access. You are getting all the benefits of the routed access, which means for the overlays, the underlay is based on the routed access. So we are completely eliminating spanning tree. We are having a benefit of the high convergence. And we can stretch VLANs across. Also, with the overlays, what we are getting is ECMP, right? So we can leverage the full capacity of the network because we can leverage ECMP from the underlay perspective. One of the examples of the overlays is software-defined access, SDA. It can be also EVPN, which supports that. Now, software-defined access is controlled and orchestrated by the DNA center controller. And DNA center is actually expressing and translating the business intent into the configuration. And there is also ICE component. And ICE component is responsible for the security, for authentication, authorization, and for the segmentation. So that's all when it comes to different options you might have from the design perspective. Now let's move into the foundational services. So all the different building blocks and all the kind of puzzle that we will put together actually to drive the network resiliency and scalability and convergence. So with that, I'm going to hand off to my colleague Jarek.
All right, so we're going to shift our gears a little bit, and we're going to start talking about foundation services. What Marcin presented it on the high level. He gave us the overview of the most important things. Now, I'm going to try to turn these high-level design principles into individual features that we can enable in our network in order to achieve hierarchical, scalable, resilient, and fastly converged network. We're going to start with the things which do influence layer 1. We're going to move through most important features on layer 2, and then we're going to end up on the layer 3. And one of our goals is to show you how enabling individual features and tuning them up can influence the convergence time. We're going to try to show that sub-second convergence is possible, and we'll try to demonstrate what things need to be enabled in order to make it happen. So let's start with the first, best practices around layer 1 physical things. And here I would like to call out 2 things. I want to start from discussing, reviewing link debounce and carry delay timers, and then I'm going to move on into the building point-to-point interconnections in between, for example, our distribution layer. So let's start with link debounce and carry delay. These 2 timers serve the same purpose. Their role is to delay signalization of link changes from the individual interface to the iOS level. Their primary meaning is to avoid unnecessary updates in case of some unexpected changes, link flaps. And when it comes to the modern iOS versions, link debounce, the default link debounce value for interfaces which are running on the gig interface, on the 1 gig and 10 gig and above, is set to 10 milliseconds. However, if we look at the link debounce timer for some pre-gig interfaces, there was a big difference in between copper connections and fiber connections. Fiber connections are also set to 10 milliseconds. However, the copper connections are set, the default value of link debounce is set to 300 milliseconds, which means that if you follow some of the instructions that we're going to present here, you're going to put a pile of switches in your lap and start playing with different features, you're going to see that your results will be off by 300 milliseconds. And the most common reason for that is because you use copper connectivity and default link value. The similar story goes with carrier delay. For modern iOS's, carrier delay is set to 0 by default. However, if we actually go and review our CVD design guides, you're going to find there a statement that it's still recommended as one of the best practices to hard-code the value of carrier delay for critical interfaces. Why? Just to ensure desired behavior. Just to make sure that our interfaces truly react and behave in a way we want it to behave. The next thing that I would like to mention is the way how we build our L3 agency, for example, in between distribution devices. We have 2 options. We can either use and rely on purely L3 routed interfaces, or we can stretch a trunk in between them and configure SVI. However, there is one thing that we should keep in mind. If we follow the first method, the time, if we look into a logs and we measure the time that it takes from the interface status change till the moment, for example, the routing updates are triggered, is going to be around 8 milliseconds. However, if we build our L3 agency in the second way by leveraging SVIs, our time needed from the interface change until we start triggering our routing updates will be measured on around 150 to 100 milliseconds. And the reason for that is the auto state. which is the mechanism which kind of go through every single interface on our switch that belongs to a certain VLAN and kind of make sure that there are no other interfaces left before actually shutting down the SVI. So that's another way or another tip that can save you up to 200 milliseconds when it comes to convergence. All right. Marcin mentioned, if you can, don't use spanning tree. Well, it's not the spanning tree that is the problem here, but it's more about the recommendation to build networks where we mitigate or where we limit the possibility of creating L2 loops. But what if we don't have such a chance? If we don't have such a possibility, like situations where we need to stretch VLANs, what are our options? Here, I want to expand a little bit on the concept of spanning only VLANs that are actually needed. Talk also about different choices behind using the spanning tree version, and also mention about the advantage that spanning tree toolkit is offering to us. And of course, when it comes to spanning tree, it's usually applicable to our access layer. So span VLANs where you have to. We have two approaches. And the rule that Marcin mentioned, so following the rule where VLAN equals access device equals subnet, it's something that can save us a lot of troubles. Because if we actually follow the rule, then we have some unique features. First of all, we eliminate possibility of having a loop. With this approach in between our distribution and access, simply there is no chance for loop. We span L3 interface between our distribution, and we kind of eliminate the chance that even if something will go wrong, we're going to have a loop in our network. What's more, there is also a nice benefit coming from the fact that we do not have blocked links, meaning we are able to fully leverage the bandwidth coming from both uplinks from a particular access device. And of course, if we don't have the chance of following the rule, which you're going to hear today a lot, VLAN equal access device equal subnet, then we don't have another option than to span additional L2 interface in between our distribution devices and put some interfaces into blocking state. When it comes to, if we come to the point where we have no other choice and we have to rely on spanning tree, what's the best mode to choose? Of course, the best mode is rapid spanning per VLAN spanning tree plus. This is the mode in which we have the best convergence time based on the proposal agreement mechanism where we no longer rely on counters, and that's where we can get a convergence of our topology in sub-second level. But how many of you still have switches that are not rapid spanning tree capable? All right. I see that we have audience who recently went through the lifecycle refresh, which is good. One of the principles of taking benefits of rapid spanning tree is making sure that all our devices in our network are rapid spanning tree capable and are working in this mode. Rapid spanning tree indeed is backward compatible and can work with non-rapid spanning tree devices, but in such a situation, we are losing the benefits. Rapid spanning tree falls back to spanning per VLAN spanning tree behavior, and then we are losing the benefits of having all the good things that comes with proposal agreement mechanism. And of course, if we have a very large-scale deployment, then MSTP is our friend here and can help us to provide a really large deployments where the number of logical ports is up to 30,000 logical ports. But with MSTP, we have to follow, or the MSTP works the best if our logical topology equals physical topology for our VLANs. This is the golden rule for MST. If we do use spanning tree, let's use also the spanning tree toolkit, meaning let's make sure the spanning tree behaves in a way we want it to behave, that we are in charge and in control of our spanning tree. Yes, spanning tree will eventually converge if we just leave everything into default, but what we may get as a result might not be up to our expectations. So what are the options available for us? starting from primary root, secondary root macro, which can help us to which can help us to put the root in a place where we want it to be, through additional features that can help us to guarantee that our root bridge stays in a place where we want it to be. So things like root guard, loop guard, uplink fuzz, UDLD. Through also additional features that we can enable on the access layer to make sure that our access layer is also protected. And we are limiting the chances to creating a loop through the access layer. And here the mechanisms, things like BPDO guard or root guard, port fast, port security. You may wonder why we actually put here a root guard next to the BPDO guard. Well, these two features these two things have a very nice or unique way how they actually react on situations where a BPDO is being detected or superior BPDO is being detected. BPDO guard in a situation where suddenly we start to receive a BPDOs on an access port where we don't expect to receive any BPDOs, we'll just put the link into error disable state, which means that we either have to have auto error disable recovery timer configured, or we will have to get into a car, drive on the other side of campus, and re-enable the port if the situation of putting port into error disable happens on some remote location. However, when it comes to the root guard in case of detecting a superior BPDO, don't disable port, just blocks it, just ignores the traffic received on that port. So if we have a situation where it typically happens in the conference rooms, where someone just has a great idea of plugging some unauthorized device, some root device, and creates a loop because of this, usually people go, OK, let's try first port. The port goes on and then goes off again. Let's try another one. And then we are being called with the information that none of the ports in the conference room is operational, and we have to react on it. So in such a situation, usage root guard will protect the root traffic from appearing on the port, and will automatically recover forwarding state in a situation where we're going to cease receiving superior BPDOs on such a port. And I mentioned also here port security, and I treat port security as our last line of defense. Why? Because both BPDO guard and root guard are based on a need of receiving some BPDO. Then these features kicks in. But what about some white box switches which actually consume BPDOs? It happens, right? In such a situation, neither BPDO guard nor root guard won't help us. In such a situation, port security might be our last line of defense to protect from really having a massive loop in our network because of such action. All right, let's move on. Best practices around trunk configurations. Trunks help us to avoid pulling additional cables in between our access and distribution layer. Thanks to the trunks, we can limit the number of cables that we actually have to install. And there are still a few things that we can configure around trunking that can help us with our convergence. So one of the first things that I would like to mention here is protection from VTP bomb. I'm pretty sure that some of you have experienced the VTP bomb in your history. If you did, please raise your hand. It's definitely a higher number of hands in the air than when it comes to non-rapid spanning tree capable devices. And yes, that happens quite a lot, that maybe we decommission some device from the network, then we put it into a storage, and then we had idea to test something, we plug it back, we started to play a VLANs, and boom, our network is not longer operational. For such a situation, putting or configuring VTP transparent mode or disabling VTP can help us with let's call it securing our network from operational errors. Also, prune VLANs which are not needed, right? That is a recommendation that helps to limit our vulnerability for creating a loop. And last but not least, keep in mind that actually disabling DTP, putting in switch port no negotiate can help us up to 2 seconds in our convergence time. So if we really want to chase down the milliseconds, here there are 3 seconds which we can gain by this configuration. When we are talking about layer 2 or staying still with layer 2, UDLD is typically deployed on fabric connections. We can either configure it in the global mode or per interface mode. And the feature is meant to help us with detecting unidirectional conditions, situation where because of bad fiber or because we've used some media converters which are not functioning properly, we have a one-link communication. And the reason why UDLD is mentioned here is because it's predominantly L2 feature and is meant to protect us from situation where we are unexpectedly moving because of lack of receiving a PDU port from, let's say, blocking from the blocking into forwarding because we no longer receive BPDUs. UDLD is not really a very fast protocol. It works by default on 15 seconds timers, and we have 2 basic modes to choose from, either aggressive one or normal one. The difference is related with the way how we react on detecting unidirectional communication conditions. In the normal one, we'll just disable our end, and the other side should see the interface going down. With the aggressive mode, we should arrow disable both ends. So again, if we have some far remote location, and UDLD will happen, and our arrow disable recover is not configured, we'll have to go and unshut the interface. Staying still and continuing with layer 2, when we talk about foundation services, there's no way not to mention about Ether channels. This is the primary way of gaining or increasing our bandwidth capabilities in between individual layers. We have different protocols. We can choose either PAGP or LACP if we want to achieve some interoperability. Typically deployed in power of 2, right? 2, 4, 8. And something that I would like to mention here is when it comes to Ether channels can work both as the layer 2 Ether channels and layer 3 Ether channels. What is important to remember is that when we configure, when we leverage Ether channels, to choose right load balancing model. Because by default, we use source MAC address, which may lead into some unequal loading results. Meaning, typically or historically, when it comes to the profile of our traffic, typically the traffic was exchanged east-west in between hosts on the access layer. Now with the applications being migrated to cloud, to centralized data center, our profile of traffic is changing more for kind of north-south connectivity, meaning we are communicating more with the applications which are outside of our campus network or the applications that are in our data center, rather than in between the individual hosts that are within the same campus network. So if we leave the default settings, source MAC address, especially when it comes to traffic which returns back from our default gateway, it's going to be all sourced from the same MAC address. So from that perspective, it's worth to tune it up and make sure that we are leveraging not only source MAC address information for load balancing, but we also take into account L3, L4. Our switches are offering quite a big variety of different options to choose from. So this is when it comes to load balancing for layer 2. OK, something happened to my clicker. Oops. Oh. OK. I'm going to use manual clicker now. When it comes to load balancing through L3 Ether channels, and we are slowly migrating toward L3 services, we have to keep in mind that Ether channels help us to reduce peering complexity. However, if we use L3 Ether channels, we might have different reactions on situations where one of the link members is failing. If we use OSPF in such a situation, OSPF, with the assumption that we've adjusted the auto-reference bandwidth, will react on such a situation where, for example, this port channel that goes in between write distribution switches, distribution switch and core switch, one of the members will go down. However, when it comes to AHIP might not react on it. It's related with the way how metrics are calculated, whether we use 32-bit metrics, standard one, or whether we are using a gig interfaces or 10 gig interfaces. If we really have port channels based on high bandwidth ports, then we might need to adjust our routing protocol to make sure that our routing protocol is capable to react on potential single link member failures. Otherwise, we may end up with overutilization. If we have exactly the same metric, if we talk about this situation where we have alternative path from reaching from core from this and this, if here we're going to have exactly the same metric, but actually different bandwidth, we may overload one of the port channels. So this is something worth to keep in mind and adjust according to the situation that is in your campus network. Talking about Ether channels and bandwidth, there are questions like, what are the typical oversubscriptions, or what are the ratios that we should follow when it comes to building, planning capacity in between access to distribution and distribution to the core? The rule of the thumb is that the oversubscription, typical data oversubscription from access to distribution is 20:1, and from distribution to core 4:1. However, it's evolving, it's changing, because the profile of our network, profile of the traffic in our network is also changing and evolving. And as I said, nowadays we see more traffic flowing east-west rather than, we see more traffic flowing north-south rather than east-west. That's why these values have to be adjusted as well. If we take also into account factors like, for example, usage of mgig ports, plugging modern access points, if we look at the example of typical 48-port switch where, for example, 12 ports are mgig ports capable of running at 10 gig and 36 remaining ports are running at 1 gig, and the typical deployment model is based on using 2 10 gig uplinks, the oversubscription for such a setup is 8:1. Right? All right, so we covered the L2. Let's move on to layer 3. What are the best practices that can help us to build, again, reliable, stable, fastly converging network? Few things to mention here, and L3 is typically used in between distribution and the core. This is where we typically leverage L3 routing. Well, first, and I would say far the most rule, is to build triangles, not squares. What does it mean? If we compare these two designs with each other, links in between distribution and the core is failing. In this situation where we've built a triangle, where we follow the triangle rule, we have all the information to perform switch over to alternative path already available on this box. We can perform hardware-based fast recovery, which is always faster than anything depending on the control plane. Here, in this situation, where this link goes down, and let's say we are using, for example, ARGIP, as a response for this, we will have to send a query, wait for the response from our neighbor, and then start our process of recovery. That will be always slower than having a pre-programmed information in our hardware tables, which can allow us to switch over, perform, choose the alternative path in really fastest possible way. And well, one of the best advantage of this is that we don't need to recalculate any path. We don't rely on OSPF ARGIP to tell us what are the alternative options here. When you configure IGP, it's also worth to consider limiting IGP peering, meaning choosing only this interface where we actually want to establish some IGMP relation, and either by configuring default passive mode for all interfaces and unpassive those that we want to leverage for our IGMP agency, or just configuring passive on all other remainings which are not used. We have these two options. This is something that helps us to limit memory usage, CPU requirements, and also helps us to limit the overall IGP overhead in such a situations. And also is some sort of a security mechanism which prevents us from unauthorized IGP peering from someone who just started to play with IGP on its own device. Marcin mentioned it. I would like to expand it a little bit more. Summarization in distribution. So let's consider the situation where we have a link failure. Yeah, so we have a situation where this link goes down. As a response to such an event, the right distribution switch will start to send AJP queries. And these AJP queries will be propagated to the peer, from the peer to the core, and then from the core to the peers of the core. And then we will have to wait for the full convergence until we will be able to reprogram our alternative path through the peering distribution device. If in this situation we use summarization, then let's see how the situation is changing. In this situation, if we have exactly the same link failure, what happens next is, yes, we have exactly the same, we follow the same path, we start sending queries, but what happens next differs. Because our core devices say, hey, dear distribution, you just told me you know everything about the subnet, right? I'm not going to send any further queries. You told me you know everything about it. So they just respond immediately. And the time needed for the convergence is limited for exchanging the query message just in between these devices, instead of depending on the response coming from outside. So this is something that helps to achieve convergence, again, in a way faster way comparing to standard configuration where summarization is not used. If we talk about assuring and making sure that we have a bidirectional configuration, I talk about UDLD. But UDLD works on layer 2. What if we need to verify a connectivity not on layer 2, but on layer 3? Then BFD is our friend. BFD can help us to react on potential disturbances in our communication path on the level of milliseconds. BFD is capable of working not only between L2 adjacent devices, but can also work over things like Metro, Ethernet, MPLS, VPLS, pseudo-wire things, right? And supports single hop, multi-hop. And what's more, BFD can be already combined together with some upper layer protocols, allowing us to triggering potential changes way faster than when we rely on a standard dead timer from our IGP routing protocol. And when it comes to Catalyst 9K, which is the base for modern campus networks, the recommendations or the most recommended values to use for BFD is 250 milliseconds with multiplier 3 on the physical interfaces and 750 milliseconds for SVIs. When we talk about L3, I want to also mention a few words about first hop redundancy protocol. This is the standard method to make sure that we don't have a single point of failure in our network. HSRP, I would say, is the most common. It's based on the virtual IP address, which is associated with virtual MAC address. However, this virtual MAC address is used only by the active device in a given moment. It serves the purpose. However, we have to keep in mind that with HSRP, we have utilizing in such a situation only 50% of our network. right? And the other router is just standing by. If we want to change the situation, then GLBP is an option for us. GLBP is relying on the same concept, however, with the assumption that each of the GLP members has own virtual MAC address. And by distributing the responses for first hop IP, we can provide different virtual MAC addresses, thanks to which we achieve load balancing. And when it comes to convergence, because I talk a lot about convergence, yes, we can debate how fast we can tune up the timers. However, for GLBP, we have to keep in mind that GLBP will be always at least 50% more effective, because in a situation where we have 2 members of given GLBP group, 50% of hosts associated with this second member will be unaffected by any potential changes. So no matter how fast we tune up the counters with GLBP, we will reduce the impact of the potential problems by 50%. However, there is one thing that we have to be aware, that in case of using or spanning a VLANs in situations where we have some ports put into a blocking state, we may deal with situation where the packets from hosts towards the first hop gateway may go through 2 hops. Yeah? And what's the solution here? VLAN equal access device equal subnet. If we have this rule, we don't have to deal with this problem, or relying on HSRP with additional configuration tune-ups, kind of helping us to making sure that the ports that goes towards the active member are in the forwarding state and going to the standby are in blocking state. All right, so that was truly the foundational services. Things which might be known, but I try to put them in a little bit different perspective and explain what are the benefits from some of the combinations that are available for us. I want to move on into campus design best practices and call out here a few things which I believe are important to mention that may influence the way how we design our campus network. All right, daisy chaining. That's a quite common problem. We are all in agreement, I guess, that for the truly hierarchical design, the best is to pull a separate cable from every access device to distribution. But what in situation where we cannot do it because it's too costly, or there is simply not a possibility to pull additional set of cabling in between given destination, and we have a need of expanding our access layer capabilities? Typically, we do this. We daisy chain switches, right? But well, if we follow a design like this, where we have, for example, L3 link here installed in between our distribution devices, when we have a failure here, we have 50% of chances that our traffic will be lost in certain configurations. So probably the next thing that you will ask is, Jaro, wait a minute. Okay, it's difficult to pull cables in between. For me, it's difficult to pull additional cables between access and distribution, but I can pull as many cables in between individual access devices. So why can't I just do this? And the answer is, yes, you can. But guys, do you remember what Martin said? Predictability. This is one of the very important aspects of our network. We want to know how our network will react in case of a potential failure, link failure. Doing things like this may not really serve the purpose of predictability. So what's the solution for this kind of things? Well, I would say one of the best is using a Cisco Stackwise technology that allows us to stack multiple access switches together, up to 8 members, which also gives us a benefits of, for example, using multi-chassis Ether channels that are combined out of the members that comes from different stack members, right? Stackwise technology is offering us, beside these benefits, also gives us superior backplane bandwidth. By saying superior, I mean if we compare potential bandwidth that we could have using front panel ports, right? Starting from the lowest platforms, 90 to 100, where the lowest possible option is 80 gig, it might be quite difficult to even achieve 80 gig of bandwidth between access layer using front panel ports, if it's possible to achieve at all. And then if we look at the other platforms from the platforms meant for the access, Stackwise for Catalyst 9300 is offering us up to 480 gigs. And when it comes to latest products, Catalyst 9300X, we have up to 1 terabyte of stacking capability, right? Which is no match for any usage of front panel ports for building connectivity between access devices. So Stackwise is technology meant for access. For distribution in the core, we have an equivalent called Stackwise Virtual, which is, well, based on the same principles, where we combine 2 devices. Here, for Stackwise Virtual, we have a possibility to combine only 2 devices together, not 8, as in case of the access layer. And out of these 2 devices, we form one single logical device, if I can call it like this. The connectivity in between them is called Stackwise Virtual, and here, in this case, we actually use front panel ports. But if we design it right, this link, by design, this link is used both for control plane and for the data plane forwarding. But if we design our network right, if we design our Stackwise Virtual setup in a right way, this link, no matter how many front panel ports we put there, normally will stay idle, not used, or used only for synchronization purposes. Why? Because Stackwise Virtual helps to solve a lot of issues that we talked about earlier. So it eliminates the problems with spanning tree, with a need of putting first sub redundancy protocols. We are using exactly the same IP address on both devices. It also gives benefits of, for example, leveraging multi-chassis Ether channels. It optimizes convergence when it comes to the all type of switchovers that can happen. And basic rule for Stackwise Virtual is making sure that everything is dual-homed. If it's dual-homed, it means that both members are actively forwarding traffic. And the Stackwise Virtual link is not used at all. Stackwise Virtual link will be used only in case when we have to reroute a traffic in case of some failure. If we design our network right and we make sure that everything is dual-homed, then Stackwise remains idle or almost idle, where only the signalization protocol is kind of making sure that both members are fully in sync in terms of the control plane. All right, moving on, since we're talking about the best practices, one of the problems that we may face is asymmetrical routing. And asymmetrical routing, especially for distribution access connectivity, may have some unexpected consequence in terms of unicast flaring. Okay? So what is the mechanism behind this? Let's assume that we are using HSRP, right? Which means that by default, only one of the distribution switches is responsible for forwarding traffic. So when it comes to a situation where we send something from the host further up, then we always send it through the right distribution member, right? But in case of asymmetric routing, if the traffic returns from the left one, we deal with a situation when, at the beginning, when our hosts are connecting to a network, we go through ARP resolution process, meaning hosts are trying to discover what is the MAC address of their default gateway, right? The hosts learn about the virtual MAC address used by the active distribution switch, start forwarding a traffic. This is the moment when, by receiving ARP requests, ARP replies, also our left distribution unit learns about the MAC addresses and the IPs used by individual hosts. But because the traffic continuously flows through the active one, the left one is not refreshing its own TCAM table when it comes to MAC addresses, but still has a valid ARP entries. And the timer for the MAC address is 5 minutes. The timer for the ARP is 30 minutes, right? So in a situation where the traffic is returning, this host, or sorry, not this host, this distribution device knows what is the destination MAC address associated with given IP address, but does not know the location of the MAC address, which in such a situation does what switches do in case when they are not aware of the port for a given MAC address. They just flood the traffic. And we have a lot of unnecessary bandwidth consumption across our entire distribution access layer. So what is the solution for that? We have few. Well, we can tune up the ARP and TCAM tables and unifying them. So when the MAC address is expiring, our ARP will expire as well, and then the left distribution switch will have to go through the ARP resolution process, and then it's going to be the opportunity for the left distribution switch to learn the location of given source MAC address. That's one way of dealing it. The other one is playing with routing metrics, removing some equal cost routing, right? Because this asymmetric routing might be a result of some ECMP happening between core and distribution as well. And of course, the other, the other way is to following a method VLAN equal access equal subnet. Then, if we follow this method, even if we deal with a situation where the standby device is receiving asymmetric routing, then this device will flood the traffic through the links where the VLAN is allowed. If we prune all our VLANs, it means that this traffic will be flooded only towards the switch where the host actually is located, which means we no longer deal with flooding. Yeah? So this rule of VLAN equal access device equal subnet has a lot of nice benefits on multiple levels, right? And of course, if we do follow the method of VLAN equal access equal subnet IP, then for us, migration towards the routed access concept becomes extremely easy. And if we migrate our network to routed access, we are just one small step from being ready for implementing more advanced concepts like SDA, EVPN, all other overlay services, which can help us back achieve some stretched VLANs if this is our desire. Of course, we have to be aware that there are some difficulties with this model, and I'm not trying to hide it. We are losing a flexibility in direct configuration, and we have some additional overhead in IP subnetting planning in such a situation. As we are getting close towards the end, I would like to mention about one more important thing, QoS in our campus network. Some say that if we have a well-designed campus network, QoS is not needed at all. I cannot disagree with those voices more. Because QoS is needed, yes, if we have oversubscription. This is something that we kind of feel naturally, that QoS will help us to choose if we have too much traffic that we try to send through one pipeline. QoS can help us to choose which traffic will be sent first and which last. But for situations where we have interface speed differences, traffic is arriving through 100 gig and is going out through a 1 gig interface. In such a situation, even a milliseconds delays in packet forwarding may have a negative consequences for applications. And drops for media-rich applications, for example, 4K streams, these applications are very sensitive for single packet drops. So QoS in such a situation can help us, can protect a traffic and make sure that we are sending out with a priority what's actually critical for us. Designing good QoS strategy is a beast by itself, and it takes a lot of considerations to do it right. Probably the most important step in this process is to take a piece of paper and put our strategy and kind of think about strategy, what applications are truly critical, business relevant, what applications are not that relevant, what applications should be treated, let's say, with the default treatment. And with QoS, I would say this is the most difficult step. Once we have this figured out, then things become way easier. Because the next step is to understand actually the QoS capabilities of the platforms that we have in our campus network. And when it comes to individual switching platforms, QoS is highly dependent on individual line cards platforms capabilities. If we decided to build our campus purely on Cat9K switches, we are safe, because all catalysts Cat9K have almost the same QoS capabilities, the same number of queues. The task of building QoS strategy on the network where we use the same platform is way easier comparing to situations where we have to deal with catalysts, maybe some legacy catalysts, maybe we also have some Nexus installed somewhere. Then we have to make sure that we truly understand these capabilities and match our strategy against individual platforms. And then, once we figure it out that part, we should always remember that QoS, in order to work fully, have to be done bidirectional. But don't worry. If you are not a true expert, if you are not very advanced in building QoS strategy, our DNAC center can help you achieving this, because no matter if you use SDA or you don't use SDA, our QoS, our DNAC is capable of translating the high-level business goals into individual QoS configuration meant for individual platforms. And with that, let's wrap up our session and let's go to conclusions, which will be the highlights from what both me and Marcin presented during the session. And here, I'm going to repeat the statement that without a rock-solid foundation, the rest doesn't really matter. Let's make sure that our network is hierarchical. In hierarchical network, each layer has a very specific role. Let's leverage the modular topology, building blocks, which are easy to grow, easy to understand, and help us tremendously in our troubleshooting efforts. Something that, from my perspective, is extremely important, that I can use exactly the same set of tools to fully understand the full forwarding path in between point A and point B. Also, relying on the modular building blocks help us to create smaller fault domain, create clear demarcation points in between potential faults, and it's also something that helps to promote load balancing and promote deterministic patterns, leveraging both the best sides of L3 and L2 technologies. With that, I'm going to repeat the statement. If you fail to plan, you plan to fail. I hope that the information that we shared today with you will help you to plan your networks. At the end, I would like to also encourage to complete the session survey and encourage also to explore other options that are available for your continuing education throughout our Cisco Live event. With that, I would like to thank you very much for your attention. I understand that this is very late and your day was full of events, so thank you for staying with us.